Hi everyone, I'm Christina and welcome to video 6 in our A-Level Mathematics Calculus series. In this video, we are differentiating trig functions from first principles, and this is part 1. So our objectives for this video are to use the definition of the derivative from first principles, which we've been looking at in the previous videos in our calculus series. And we're going to use our derivative to differentiate simple trigonometric functions. We also want to link the differentiation of trig functions to a new concept called small angle approximation. So these are going to be very important in finding the derivative of our trig functions from first principles. And in this video, we're going to focus on the derivative of sine x. So we are going to find the derivative of sine x from first principles. So let's first make a note of our function f of x that we want to differentiate, which is sine of x. And let's make a note of our derivative. So f dash of x, as we've seen in our previous videos, is the limit as h tends to 0 of f of x plus h minus f of x all over h. And so we have our function f of x, that's just sine x, but now we want our f of x plus h. So to find f of x plus h, we just substitute in x plus h into our function. So this x plus h becomes our new x, and so we have sine of x plus h. Now recall from our trig series, of videos, that sine of a plus b equals sine a cos b plus cos a sine b. That's our compound angle formula for sine. So if you notice, sine of x plus h, now that's sine of a compound angle. So we can rewrite that using our compound angle formula for sine that we looked at in our trig series. So sine of x plus h is equal to, let's follow the format here, sine of x cos of h, put brackets around that so we don't think it's cosh, plus cos of x sine of h. So now that we've written it like that, we can use our functions f of x and f of x plus h to find the derivative. So then f dash x equal to the limit as h tends to 0 is sine of x plus h minus sine of x over h. And just to make it super clear, that's our f of x plus h, and sine of x is our f of x. And so we can rewrite it as sine of x cos of h plus cos of x sine of h minus sine x all over h. So once we get to this point, we're a bit stuck. So we need to introduce our small angle approximations for sine theta and cos theta. So what these tell us is that sine theta tends to, or rather sine theta is approximately theta for very small angles of theta. And we write that as for angles of theta much smaller than 1. and then cos theta is approximately 1 for small angles of theta, and we write that as 4 angles of theta much smaller than 1. So if we apply our small angle approximations to our limit for our derivative here, if I first rewrite this and I divide each of these terms by h first, so I'll write that as sine x cos of h over h plus cos x sine of h over h minus sine x over h. We can see here that h is very small. It's a very small angle because h is tending towards 0. So we can apply our small angle approximation here. So let's think about cos h in our first term. Well, from our small angle approximations, cos of theta is approximately 1. So cos of h, as h tends to 0, is also approximately 1. We can approximate it to 1. So then sine x cos h just becomes sine x over h. Now, cos x sine h over h, this term becomes, well, sine theta approximates to theta. So then we can write sine h here as h. And we can write that entire term as cos h times h over h. Immediately we can see h cancels. And then our last term doesn't really change. It's just sine x over h. And immediately you can see sine x over h minus sine x over h. Brackets around that as well. So those two terms cancel, and we're just left with cos of x. And so our derivative f dash of x is cos of x for the function f of x equals sine of x. So now we've differentiated sine of x from first principles to show that its derivative is cos x.